Welcome! Today, we'll be tackling an exciting problem from LeetCode, problem number 1252, cells with odd values in a matrix. In this challenge, we'll explore how to manipulate a matrix based on specific operations and calculate the number of cells with odd values. Let's dive in. In this problem, you are given an m by n matrix where all the cells are initially set to 0. Along with this matrix, you are provided a list of indices. Each index in the list represents a pair of row and column coordinates, and for each pair, you are required to increment all the cells in the specified row and column by 1. After performing all the operations described by the indices, the task is to calculate how many cells in the matrix contain odd values. The input includes the dimensions of the matrix M and N, which can range from 1 to 50, and the list of indices, which can have up to 100 pairs. Each pair in the indices list is valid, meaning the row and column values fall within the bounds of the matrix. The output is a single integer that represents the count of cells with odd values after all operations are applied. Let's consider an example where the matrix has 2 rows and 3 columns, and the indices list contains 2 pairs, 0, 1, and 1, 1. Initially, the matrix is filled with zeros, so it looks like this: 0, 0, 0, 0, 0, 0. When we process the first index, 0, 1, we increment all the cells in row 0, making it 1, 1, 1. Then, we increment all the cells in column 1. Adding 1 to the corresponding cells in row 1 results in the updated matrix, 1, 2, 1, 0, 1, 0. Now, let's apply the second index, 1, 1. First, we increment all the cells in row 1, turning it into 1, 2, 1. Next, we increment all the cells in column 1 again, which also affects row 0. After these updates, the matrix becomes 1, 3, 1, 1, 3, 1. Finally, to determine the output, we count how many cells contain odd values. In this case, there are 6 such cells, so the output is 6. This illustrates how both row and column increments interact to change the matrix. Let's explore another example with a larger matrix. Here, the matrix has 3 rows and 4 columns, and the indices list contains 3 pairs, 0, 2, 1, 3, and 2, 0. Initially, the matrix is filled with zeros, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Starting with the first index, 0, 2, we increment all cells in row 0, resulting in 1, 1, 1, 1. Then, we increment all cells in column 2, which affects rows 1 and 2. The updated matrix looks like this: 1, 1, 2, 1, 0, 0, 1, 0, 0, 0, 1, 0. Next, we process the second index, 1, 3. We increment all cells in row 1, making it 1, 1, 2, 1. Then, we increment all cells in column 3, affecting rows 0 and 2. The matrix becomes 1, 1, 2, 2, 1, 1, 2, 1, 0, 0, 1, 1. For the third index, 2, 0, we increment all cells in row 2, turning it into 1, 1, 2, 2. Then, we increment all cells in column 0, which affects rows 0 and 1. The final matrix is 2, 1, 2, 2, 2, 1, 2, 2, 1, 1, 2, 2. Counting the odd values, we find there are 8 cells with odd numbers, so the output is 8. Finally, let's consider some edge cases. For the minimal input case, where m and n are both 1, and there is a single index, like 0, 0, the matrix has only one cell. After applying the single operation, this cell will contain the value 1, which is odd. The output in this case is 1. Another edge case is when all operations cancel each other out, leaving no cells with odd values. This can happen if rows and columns are incremented multiple times, balancing each other out. Lastly, when there are multiple overlapping operations, careful handling is required to ensure all increments are applied correctly without missing or double counting any changes. To solve this problem, one possible approach is the brute force method. The idea is to directly simulate the operations described in the problem. We start by creating an mxn matrix filled with zeros. For each pair, r_i, c_i, in the indices array, we increment all the elements in the specified row r_i and all the elements in the specified column c_i. Once all the operations have been applied, we iterate through the matrix and count how many cells contain odd values. While this method is straightforward and easy to grasp, it has significant computational costs. The time complexity is proportional to the number of operations in indices multiplied by the sum of the number of rows and columns, which can become very inefficient for larger matrices. Additionally, the space complexity is high since we are storing the entire matrix in memory. This makes the brute force approach impractical for large datasets, even though it is simple to implement and understand. Instead of directly manipulating the matrix, the optimized approach leverages auxiliary arrays to track the increments. The key insight here is that we can avoid updating the matrix entirely by maintaining two arrays, one for rows and one for columns. These arrays, row and col, keep track of how many times each row and column is increment. For each r_i, c_i in the indices array, we simply increment the corresponding values in row, r_i, and col, c_i. Once all indices have been processed, we compute the value of each cell using the formula matrix, r, c, equals row, r, plus col, c. A cell is considered odd if the sum of row, r, and col, c, is odd. This approach allows us to count the odd cells without ever constructing the full matrix, significantly reducing computational overhead. By focusing only on the increments, we streamline the process and make it much more efficient. The optimized approach offers clear advantages in terms of complexity. The time complexity is reduced to O, len, indices, plus m*n. The first term accounts for processing the indices array, while the second term is for checking each cell to determine if its value is odd. Space complexity is also improved, as we only need two arrays of size m and n, resulting in O, m plus n, space usage instead of O, m*n. This is because we are no longer storing the entire matrix. The most important observation here is that the final value of each cell depends solely on the sums of the increments for its row and column. By avoiding direct updates to the matrix, we eliminate unnecessary computations and reduce memory usage. Given these efficiency gains, the optimized approach is a clear improvement over the brute force method, especially for larger matrices and longer indices arrays. Every solution involves trade-offs. The brute force approach is simple and easy to implement but becomes inefficient as the size of the input grows, due to its high time and space complexity. On the other hand, the optimized approach is slightly more complex conceptually, but it is far more efficient in practice. It avoids the overhead of updating the matrix directly and reduces memory usage by relying on auxiliary arrays. This makes it highly scalable for large datasets. While the optimized approach may require a bit more effort to understand initially, the significant improvements in performance and efficiency make it the ideal choice for this problem. By striking the right balance between clarity and computational efficiency, this strategy ensures that we can handle even the most demanding scenarios effectively. In this problem, we start with an mxn matrix filled with zeros and an array called indices where each element is a pair, r_i, c_i. The task is to increment all elements in row r_i and column c_i by 1 for each pair in indices. After processing all pairs, we count the number of cells in the matrix that have odd values. Let's take an example where m equals 3, n equals 3, and indices equals 0, 1, 1, 1. Initially, the matrix is a simple 3 by 3 grid of zeros. To solve this problem, we can first simulate the process in a brute force manner. This involves iterating through indices and incrementing the appropriate rows and columns directly in the matrix. This gives us a clear starting point to understand the mechanics of the problem. To implement the brute force simulation, we take each pair, r_i, c_i, in indices and increment all elements in the respective row and column. For example, if we process the pair 0, 1, we first increment all elements in row 0, resulting in 1, 1, 1. Then, we increment all elements in column 1, updating the matrix to reflect these changes. After processing 0, 1, the matrix looks like this: 1, 2, 1, 0, 1, 0, 0, 1, 0. We repeat this process for the next pair, which is 1, 1. After completing all the updates, the final matrix is 1, 3, 1, 1, 3, 1, 0, 1, 0. The last step is to iterate through the matrix and count how many cells contain odd values. Here, the odd values are found in 6 cells, so the final result is 6. While this approach works, it's not the most efficient, especially for larger matrices.
To optimize the solution, we can avoid directly modifying the matrix. Instead, we track the increments for each row and column separately using two 1D arrays, row underscoring 4 rows and col underscoring 4 columns. For every pair, R underscore I, C underscore I, in indices, we increment row underscoring R underscore I, and col underscoring C underscore A. This allows us to defer the actual computation of cell values until the end. The value at a cell, I, J, can be determined by summing row underscoring I, and col underscoring J. If the sum is odd, the cell is considered odd. This approach not only saves memory but also eliminates redundant updates to the matrix. By focusing on the row and column increments, we streamline the logic and improve efficiency. Additionally, while the brute force method uses a 2D array and has higher computational overhead, this optimized approach only requires two 1D arrays, making it more scalable for larger inputs. With the optimized approach, we use two arrays, row underscoring and col underscoring, to track the increment counts for rows and columns. This reduces the time complexity significantly. For example, given indices equals 0, 1, 1, 1, we increment the respective values in these arrays. After processing the indices, row underscoring becomes 1, 1, 0, and col underscoring becomes 0, 2, 0. To determine whether a cell, I, J, has an odd value, we sum row underscoring I, and col underscoring J, and check if the result is odd. This eliminates the need to directly update the matrix, as all the information needed to calculate the final result is stored in the two arrays. This method is not only faster but also reduces the memory requirements compared to the brute force approach, making it ideal for larger matrices. In the optimized algorithm, the first step is to initialize the row underscoring and col underscoring arrays with zeros. These arrays have sizes m and n respectively, corresponding to the number of rows and columns in the matrix. Next, we process each pair, R underscore I, C underscore I, in indices, incrementing the respective values in row underscoring and col underscoring. Once all increments are recorded, we calculate the values of each cell, I, J, in the matrix by summing row underscoring I, and col underscoring J. If the sum is odd, we increase the odd underscore count. Finally, we return the total odd underscore count as the result. This approach ensures that we calculate the odd values efficiently without repeatedly modifying the matrix itself. By focusing on the cumulative increments and performing the calculation only at the end, we achieve a significant improvement in both time and space complexity. Let's analyze the complexity of the optimized approach. The time complexity for processing all the pairs and indices is O(k), where k is the number of pairs. Calculating the odd values for each cell in the matrix takes m*n, as we iterate through all m rows and n columns. Combining these steps, the total time complexity becomes O(k) plus m*n. For space complexity, the brute force approach requires m*n to store the entire matrix, while the optimized approach only requires m plus n for the row underscoring and col underscoring arrays. This reduction in space usage is especially important for larger matrices, where the memory savings can be substantial. By balancing computational efficiency and memory usage, the optimized solution provides a practical and scalable way to solve the problem. This implementation solves the problem cells with odd values in a matrix efficiently by leveraging row and column counters. Here's a step-by-step explanation. 1. Initialization. The row underscore count and col underscore count arrays are initialized with zeros. These arrays track how many times each row and column has been incremented. 2. Processing indices. For each R, C in the indices list, we increment the corresponding row underscore count, R, and col underscore count, C. This effectively simulates the increments without directly modifying the matrix, saving both time and space. 3. Counting odd cells. Once the row and column counts are prepared, we iterate through each cell of the matrix. A cell at I, J, will have an odd value if the sum of row underscore count, I, and col underscore count, J, is odd. We check this condition using the modulo operator and increment the odd underscore count counter accordingly. 4. Returning the result. Finally, the total count of odd cells is returned as the result. This approach is efficient because it avoids explicitly constructing the matrix, reducing the space complexity from m*n to m plus n.
The time complexity is O, len, indices, plus m asterisk n, where len, indices, accounts for processing the indices and m asterisk n is the cost of counting odd cells. This makes the solution suitable for reasonably large inputs, as specified in the problem's constraints.
This is the Java implementation for LeetCode problem number 1252, cells with odd values in a matrix.
The logic mirrors the Python implementation, using arrays to track row and column increments and nested loops to compute the number of cells with odd values. Key Java-specific differences include the use of explicit type declarations and enhanced for loops for array traversal. Let's start by looking at a simple example where the matrix dimensions are 2 rows and 3 columns, and the indices provided are 0, 1, 1, 1. First, we initialize 2 counters, one for rows and one for columns. Since we have 2 rows, row_count starts as 0, 0, and for the 3 columns, col_count begins as 0, 0, 0.
Now, we process the indices.
For the first index, 0, 1, we increment the count for row 0 and column 1, resulting in row_count equals 1, 0, and col_count equals 0, 1, 0. Then, for the second index, 1, 1, we increment the count for row 1 and again for column 1, which updates row_count to 1, 1, and col_count to 0, 2, 0.
These counters now represent how many times each row and column was incremented based on the indices. Next, we calculate how many matrix cells have odd values. To do this, we initialize an odd_count variable at 0 and iterate over each cell in the matrix, represented by the indices I, j. For cell 0, 0, the sum of row_count 0 and col_count 0 is 1 plus 0 is equal to 1, which is odd, so we increment odd_count to 1. For cell 0, 1, the sum is 1 plus 2 is equal to 3, which is also odd, so odd_count becomes 2. Similarly, cell 0, 2 has a sum of 1 plus 0 is equal to 1, so we increment odd_count to 3. Continuing to the next row, cell 1, 0 has a sum of 1 plus 0 is equal to 1, increasing odd_count to 4. Cell 1, 1 has a sum of 1 plus 2 is equal to 3, so odd_count is now 5. Finally, cell 1, 2 has a sum of 1 plus 0 is equal to 1, making the final odd_count equal to 6. Thus, the total number of cells with odd values in this example is 6. Now, let's consider a larger example with a 3 by 4 matrix in indices 0, 0, 1, 2, 2, 1. To begin, we initialize the row counter as row_count equals 0, 0, 0, for the 3 rows and the column counter as col_count equals 0, 0, 0, 0, for the 4 columns. Then, we process the indices one by one. For the first index, 0, 0, we increment row_count 0 to 1 and col_count 0 to 1, resulting in row_count equals 1, 0, 0, and col_count equals 1, 0, 0, 0. For the second index, 1, 2, we increment row_count 1 to 1 and col_count 2 to 1, updating row_count to 1, 1, 0, and col_count to 1, 0, 1, 0. Finally, for the third index, 2, 1, we increment row_count 2 to 1 and col_count 1 to 1, which gives us row_count equals 1, 1, 1, and col_count equals 1, 1, 1, 0. These counters are now ready for the next step. To count the cells with odd values in this example, we start by setting odd_count to 0 and iterate over each cell in the 3 by 4 matrix. For cell 0, 0, the sum of row_count 0 and col_count 0 is 1 plus 1 is equal to 2, which is even. For cell 0, 1, the sum is 1 plus 1 is equal to 2, also even. For cell 0, 2, the sum is 1 plus 1 is equal to 2, still even. However, for cell 0, 3, the sum is 1 plus 0 is equal to 1, which is odd, so we increment odd_count to 1. Continuing this process for all cells, we find that there are a total of 8 cells with odd values. Thus, the final odd_count for this example is 8. Finally, let's analyze a simple edge case with a 1 by 1 matrix and a single index 0, 0. Here, row_count and col_count both start as 0.
processing the index 0, 0, we increment row underscore count 0 to 1 and col underscore count 0 to 1, resulting in row underscore count equals 1 and col underscore count equals 1. Now, for the only cell in the matrix 0, 0, the sum of row underscore count 0 and col underscore count 0 is 1 plus 1 is equal to 2, which is even.
Since there are no odd values, the final odd underscore count is 0.
This demonstrates how the solution works even in the smallest possible case. Here, we analyze the time complexity of the solution step by step. First, creating the row underscore count and col underscore count arrays of size m and n respectively requires m plus n time because we are simply allocating memory for these arrays.
Next, we process the indices array, which has a size of k.
For each index, we increment the corresponding row and column counters, and since each operation takes constant time, this step requires k time. Finally, to count the cells with odd values in the matrix, we use a nested loop that iterates over all m*n cells. For each cell, we compute the sum of the corresponding row and column counts and perform a modulus operation, all of which take constant time per cell. This results in a time complexity of m*n for this step. Now, when we combine all these steps, the total time complexity becomes m plus n for initializing the arrays, plus k for processing the indices, plus m*n for counting the odd cells. This simplifies to m*n plus k. Since the runtime is determined by the size of the matrix, m*n, and the number of updates, k, this complexity applies to the best, average, and worst cases alike. On the other hand, the space complexity arises from the additional memory used. The row underscore count and col underscore count arrays require m and n space, respectively. Other variables, such as odd underscore count and the loop variables, contribute only 1 space. Therefore, the overall space complexity at this point is dominated by the arrays, resulting in m plus n. Given this breakdown, the total space complexity is indeed m plus n, as the memory usage is determined solely by the two arrays, with no additional data structures involved. To understand the efficiency of this optimized solution, let's compare it to a brute force approach. In the naive method, we would initialize an mxn matrix with zeros, which requires m*n time. Then, for each pair of indices in the input, we would increment all cells in the corresponding row and column. This step involves k** m plus n time, as each update affects multiple cells. Finally, counting the odd value cells would need another m*n iteration over the entire matrix. This gives the brute force approach a total time complexity of m*n plus k** m plus n. The optimized solution avoids directly manipulating the matrix, reducing dependency on k** m plus n, and achieving m*n plus k, making it significantly more efficient. To further justify the big O complexity mathematically, consider the operations involved. The m*n term comes from iterating over the entire matrix to count odd cells, while the k term arises from processing the indices to update the row and column counters. These two operations are independent, which is why the overall complexity is additive, resulting in m*n plus k. Similarly, for space complexity, the m plus n comes solely from the row underscore count and col underscore count arrays, as no additional data structures are used. This mathematical analysis confirms the efficiency of the solution, both in terms of time and space. When working on this problem, there are a few common mistakes to watch out for. First, not updating both rows and columns for each index in the indices array is a frequent error. Remember, for every pair in indices, you need to increment all the elements in the specified row and also all the elements in the specified column. Ignoring one of these operations will lead to incorrect results because the problem explicitly states that both updates must happen.
Another mistake is attempting a brute force implementation where you iterate through the entire matrix for each operation.
This can lead to a time complexity of n squared m, or worse, which is highly inefficient for larger matrices and will likely time out on larger test cases.
Lastly, a common source of errors is misunderstanding matrix dimensions or zero-based indexing.
For example, if you confuse rows and columns or accidentally use one-based indexing in a zero-based system, your solution might access incorrect indices or even cause out-of-bounds errors. Paying attention to these details is crucial to avoid such pitfalls.
Another error to avoid is assuming that all rows and columns in the indices array are unique.
In reality, duplicate indices are common, and each occurrence should contribute to the final result. If you overwrite the effects of duplicates or fail to aggregate them properly, your output will be incorrect. Equally important is pre-processing row and column counts instead of simulating each operation directly. For example, instead of incrementing values one by one in the matrix, you can track how many times each row and column is incremented using auxiliary arrays.
This avoids redundant computations and leads to a far more efficient solution.
Both of these issues highlight the importance of understanding the data structure and leveraging efficient techniques. From an interview perspective, this problem is often used to assess how well you can optimize your code. While brute force solutions are a starting point, interviewers typically expect candidates to identify patterns and optimize to O, N plus M, using frequency arrays for rows and columns. Additionally, testing edge cases is a critical part of the interview process. For example, ensure your solution handles an empty indices array, where no operations are performed, or matrices with only one row or one column. Duplicate indices in the input are another edge case that you must address carefully.
It's also essential to explain the trade-offs between different approaches, such as brute force versus pre-processing. Highlighting how pre-processing reduces redundant computations while slightly increasing space usage demonstrates your understanding of algorithmic efficiency. Finally, always clarify the problem constraints, such as matrix dimensions, to avoid making incorrect assumptions. This problem shares similarities with other LeetCode problems that involve matrix manipulation or range updates.
For instance, LeetCode 598, Range Addition 2, focuses on finding maximum overlaps in a matrix after applying operations, which is conceptually close to incrementing rows and columns here. LeetCode 1094, Carpooling, involves tracking usage over a range of indices, which aligns with the idea of using frequency counts to manage increments efficiently. Another related problem is LeetCode 370, Range Addition, which emphasizes processing incremental changes using optimized data structures. Of course, this problem itself, LeetCode 1252, directly deals with counting odd cells in a matrix after updates, making it a foundational problem in this category. Exploring these related problems can deepen your understanding of range-based operations and help you identify patterns across different scenarios. There are several alternative approaches to solving this problem, each with its own trade-offs. One efficient method is using frequency arrays to count how many times each row and column is incremented. This approach sacrifices O(1) space for O, N plus M space but drastically improves time complexity to O, N plus M, making it suitable for larger inputs.
Another option is the brute force simulation, where you directly apply each operation to the matrix.
While simple to implement, this method is computationally expensive and impractical for large matrices.
A more advanced approach involves recognizing mathematical patterns.
By analyzing the parity of row and column operations, you can determine the number of odd cells without explicitly performing all updates.
This requires deeper mathematical insight but achieves the most optimized performance.
Choosing the right approach depends on the problem constraints and your familiarity with optimization techniques.
Great job! We've successfully solved problem number 1252, cells with odd values in a matrix.
We discussed different approaches, from brute force to optimized solutions, and highlighted the importance of analyzing constraints.
Remember to practice similar problems to strengthen your understanding of grid-based algorithms. Thanks for tuning in, and see you next time. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!